So yeah, I worked on type invariants in collaboration with Jacques-Henri and Xavier at the LMF. And I myself, I'm a student at TUM in Munich. All right, so first I'm gonna give a brief overview of Creusot for those of you who don't already know it. Then talk about the design of type invariants, Creusot, discuss its soundness, and give a few details about selected parts of its implementation before finally talking about conclusion and future work. So starting with Creusot. So Creusot is a deductive verifier for safe Rust code. This means that it takes a Rust program along with a specification and then checks whether the Rust program actually adheres to that specification. And to do that, it translates Rust programs to YML, which is the functional logic language at the core of the Y3 verification platform. And the specifications with which Rust programs are annotated are written in a special kind of language, which is called Perlite. That's a subset of Rust, which additionally supports logic operations like quantifiers or implications. And at the core of this functional translation, what enables this functional translation is the non-aliasing guarantees of mutable references that well-typed Rust programs have. And I also listed two design principles of Creusot here, which I also try to follow with or use as a guidance for the design of type invariants in Creusot. And the first principle is keep it rusty. And this means that a Rust developer should not be too surprised by how verifying Rust programs work. This is, for example, shown with the Perlite specification language, which uses a very Rust-like syntax, or also making use of existing Rust features like traits or macros in verifying programs. And the second design principle is ensuring composability, which means that we want to support as large as possible subset of Rust, and all the different features of our verifier should interact well with each other. Okay, so like I said, a central part of Creusot are prophecies, which is how Creusot translates mutable references. And a mutable reference is encoded as a pair of its current value, star R, and a prophetic final value, head R. And the prophetic final value denotes the value whatever will be in the reference at the last point, after the last time it has been mutated, the value that will be in that reference. And so after the last write to a reference, we resolve the prophecy, which means that we learn the actual value head R. And on the slide, there is an example which shows how this works. So we have a variable x and take the reference R to a mutable reference R to that value x. And in Creusot's logic, this means that R is a pair of the current value of the reference, which is just x, and the prophecy, which we don't know at this point, so we just write any. And on the other hand, the variable which was borrowed gets assigned that prophetic final value of the reference R. And then subsequently, when we update R, when we write 3 to the reference, we set the current value of the reference to 3, and the prophetic final value stays opaque. And because this was the last time we modified our mutable reference, we resolve the prophecy, which means we learn the actual value of that prophetic head R. And this works by just assuming at this point, now the current value and the final value are equal. And this means that after we have resolved R, we can prove that the updated value of x is 3, since when we borrowed x, we know that x is equal to the final value of R, and we learn the value of head R. So now we can prove x equals 3. Okay, and here's an example of how a sort function could be verified with Creusot. And it's not super important to understand exactly how this algorithm works. More important are these attributes written on this function. So the norm sort function is a sorting algorithm which works by repeatedly swapping adjacent elements if they're not yet in order. And so we put a post condition, a ensures clause attribute on the norm sort function, which says that the final value of our argument v is in fact sorted. And the interesting thing here is that there is no with Creusot's contracts, there is no pre and post state in the function, but we just to refer to values after the function, we use these prophecies to say the final value of that mutable reference will be sorted. And we also see that we have a loop, and the loop gets a invariant attribute, which says which specifies a loop invariant that must hold before the loop starts and then is preserved in every iteration of the loop. And here it just says that all the elements in V up to the index I are sorted. Okay. Now that we have seen gotten a glimpse of Creusot, I will talk about type invariants, starting with the design. So type invariants are logical predicates attached to data types and which hold for all values of that type. Just by knowing that X has type T, we can have get additional hypotheses based on the type invariant of the type. And the way we ensure that this is actually enforced is by having all operations on the data type preserve this invariant. And two typical use cases where we want this feature are, for example, implementation invariants, which is, for example, a sorted list, where the invariant would just say that, in fact, all our elements in the list are sorted. And then operations on that list, like insertion or extracting the smallest elements, would preserve the type invariant which says that the list is sorted. Another use case, which is very similar and can just as well be encoded with type invariants, is what I call predicated subtypes. And by this I mean, for example, a special kind of integer with a type invariant that specifies that all of the values are even. And the difference between the use cases is just that on the first use case, the invariant is usually opaque, and the client just cares that there's some invariant that is preserved by the operations, whereas in the second use case, the invariant is more transparent, and clients would actually want to use that special property of the type. Okay, now we have an example of a type with a type invariant, and this example also shows how to define the type invariant for the type. So we have a type sum to 10, which has two fields, A and B. And the invariant of that type is that the fields always add up to 10. And we declare this invariant by implementing the invariant trait for the type. And this requires us to define the invariant predicate. And here, as expected, the predicate just says that our fields A and B, that their sum is 10. And the predicate attribute just marks it as a logic level function. And the perlite macro enables the use of these model operators, but it's not too important exactly what they do here. Okay, now the main design challenges of type invariants. So we've seen how to define type invariants, but how to actually enforce that the types always fulfill these invariants. So the first main design question is how can we enable invariants to be temporarily broken, and how do we restore them? And this is important because operations might want to internally break the invariant as long as at some later point the invariant is restored again. And the second main design challenge of supporting type invariants in Creusot is how type invariants should interact with mutable references. Okay, so to answer the first question, our boundary for where invariants have to hold and where they can be temporarily broken are function boundaries. So here we have a function mingle, and this function takes a sum to 10 value and returns a sum to 10 value, but internally it temporarily breaks the invariant by decreasing the field A by 1 and then increasing the field B also by 1. And at the start of the function, we can in fact prove that the invariant holds just because the type of our argument is sum to 10. But then we are allowed to break it because between the two increment and decrement and increment operations, the invariant in fact does not hold. But in the end, just before returning our modified sum to 10 value, we have to prove again that the invariant of that value holds again because the function boundary, the type of the return value requires us to restore the type invariant of our value S.
Dominik, you have a question
Oh yeah, please.
from Vitotas, who's asking, are type invariants required to hold in loop invariants?
Not automatically. So right now, we thought about that, but right now it's the case that sometimes we have to manually add loop invariants, saying that a loop preserves type invariants. Does it answer the question?
Seems like it does, yeah.
Okay. All right. So how do we enforce these invariants and function boundaries? We do that by elaborating the contract of a function using the types of the arguments and the return value. So for every argument type with an invariant, we add a precondition, and for a return type with type invariant, we add a postcondition. So here for the mingle function, we add a precondition requiring the invariant of S, and we add a postcondition ensuring that the return value noted by the symbol result in fact satisfies the invariant. And so this explains how invariants are elaborated on the Rust level, but also on the Perlite level. We elaborate type invariants by guarding quantifiers. And this is shown in the second example here. So for a universal quantifier quantifying over values S of some type sum to 10, we add a implication that we only look at values S that satisfy the invariant, and P is just some predicate. And similarly for existential quantifiers, we also only consider values S where the type invariant of S holds. And these guards are generated. So if you write for all S of type sum to 10, we synthesize this guard with invariant of S.
You have another question from Julien, who asks, this would prevent some types of factorization, right? For example, extracting a function that operates on values that do not satisfy the type invariant.
Right. We have a way of, so generally we don't support having functions that do not have like open invariants of its arguments, but we plan to add a feature that functions can actually specify that they take their arguments with an open invariant. But generally, yeah, we enforce that all type invariants are closed at function boundaries.
Seems like it answers the question.
All right. Okay, so now for the second main design challenge, that's the interaction of type invariants with mutable borrows. So now we consider how we call a function that takes a mutable reference to a type with a type invariant. So here we have a function swap that takes a reference, mutable reference to sum to 10. And so to call this function, we first create a reference R of our sum to 10 value and pass that reference to swap. And the main question here is, how do we prove that the invariant of S holds after after we call swap. So the assertion after the call, our value of s, since when we borrowed s, we said that now s equals the final value of r. So to prove the assertion after the call, we need to know something about the final value of r. And the usual way how we learn the final value is through resolution. However, in this case, since we move our reference into swap when we call it, we don't resolve r in the caller. So there's two solutions how we might be able to prove this assertion. The first solution is to have a post condition on swap, which tells the caller what happens to the reference r gets. And this is the obvious approach, but there are some problems with this approach that will be discussed next. So we developed an alternative, which we call prophetic invariance. And this will be the focus of the next slides. So first, I talk about why the obvious approach of adding a post condition to swap does not work. And so we look at how we would elaborate the contract of swap. So here, we add based on the argument type, we add a precondition saying that the invariant of the current value of our mutable reference holds. And to prove the assertion in the caller, we also add a post condition which says that the final value of our reference also satisfies the invariant. And this would in fact allow the caller to prove the assertion, but for other functions, this does not work. So we look at a function generic, which takes an argument of generic type t, and again we would, based on the argument type, we would a precondition saying that the invariant of x must hold. But in this case, what should the post condition be? Just based on the type of the argument, we don't know whether it might be a mutable reference, and we might need something telling the caller what happens to the final value of the reference. And as a reminder, again, there is no distinction between pre and post state in Creusot. So the only way to talk about how a value changes in a function is using the current and final value of mutable references. But here we cannot, since x has type t, we cannot generically say or talk about the final value of x, since this only applies to mutable references. And our solution to the problem is what we call prophetic invariance. So again, we consider a similar function like before, where we call a function passing it a mutable reference. But here we call this generic function, which takes an argument of generic type t. And so here, the crew of prophetic invariance is that when we create the reference, we just assume that the invariant will hold for the final value. So borrowing becomes kind of like a promise that whatever we do with the reference, we promise that at the end, the final value will satisfy the type invariant. And here in this case,
I think Ralph might have answered his own question, or you might have answered it already, but Ralph had a quick question about the inf operator, asking how is inf for mutable reference defined? Isn't it inf holds for current and final value?
I will get to that. Just, I think, on the next slide.
Yeah.
Okay. So yeah, for now, inf just represents the type invariant of its value, and we will see more about how exactly it is defined. Right, here in this case, after the call to generic, we don't need any post condition from generic, but we can just prove our assertion by the prophetic assumption we made about the invariant of the final value. And of course, the obvious question here is, how can we ensure that this is sound? Because if we assume that the invariant of our final value holds, but this but the generic the function we call generic breaks the invariant, then this our assumption would not be justified. Right. So in the next few slides, we'll talk about how we ensure that this encoding is sound. And so we start out with exactly what Rolf asked, talking about the invariant of a value R, that is a mutable reference. And so, yeah, the invariant of a mutable reference is the conjunction of the invariant of its current value and the invariant of its final value, which also makes sense if we consider that Creusot understands mutable references as a pair of current and final value, and then we just turn that pair into a conjunction of the invariants. And then when we create a reference, we assume the invariant of the prophetic final value. And then when we resolve R, that means at the point where we know the actual value of the prophecy, and we at this point we assert that the invariant holds for this final value. So we insert a proof obligation requiring to prove that at this point the invariant holds. And again, we have we look at the contract of swap. And so here now swap gets only one precondition based on the type of its argument R, and there is no more postcondition for swap. And to summarize, the conditions for soundness based on this encoding. First, it's important that we never assume a contradictory invariant, since assuming a invariant which is trivially false would immediately introduce unsoundness, allowing us to prove incorrect programs. And the second condition for soundness is that we always resolve values with prophetic invariance. Since if we would not resolve a value with prophetic invariance, then the assumption we made earlier about the invariant of its final value would not have been justified. Okay, so now we talk a bit more in detail about each of these conditions. So the first condition was never assuming contradictory invariance. So here we have a type unsound, and its implementation of the invariant trait just defines its invariant to be always false for all values self. And in this case, if we would assume the invariant of the final value for a mutable reference to unsound, we would assume false, introducing unsoundness. And the way we prevent this is that we ensure that type invariants are inhabited, but there always exists at least one value of the type that satisfies the invariant. And this is enforced by a law in the invariant trait. And this law must be proven by every implementation of the trait. So here, this law would not be provable for the unsound type and its definition of the invariant predicate. The second condition is that we always resolve values with prophetic invariance. And this becomes especially relevant if we consider how a type with an invariant could be hidden inside another type that does not have an invariant. So in the example again, we have a value S and a reference R, and we break the invariant by writing 0 through the reference. But then we put the reference inside a vector. And in the example, we assume that we did not define or we did not implement the invariant trait for the vector type. And thus, the invariant would just be considered trivial, so true for all vectors. And then when we resolve V, we would not have to prove the invariant of the contained reference. However, we would still assume, assume that or learn the final value of our reference, And this would allow us to afterwards prove that 0 plus 7 is 10 just by using our assumption we made when we borrowed S. And so the solution here is that we always have to, that the invariant of a type must always structurally include the invariance of its constituents. So we have to force the invariant of vec to also consider the invariance of the elements contained in the vector. And so we cannot rely on the user just always giving the correct definition or implementation of the invariant trait, but we must automatically generate the right invariants for these types. And we do that by composing the invariant. So we have this inf symbol used earlier to describe the invariant of a value. And the inf predicate is actually composed of two parts: a user invariant, which is what the user declares by implementing the invariant trait, and a structural part, which is generated based on the type's definition. And the total inf symbol is just the conjunction of these two parts. So for example, for a sorted list type, which is, has the invariant that its elements are sorted, the inf symbol would be the user invariant, which says, yeah, that the elements are in fact sorted. And then the structural part, which is the thing after the right-hand side of the and here, which says that also the elements in the list all satisfy their invariance. And so we match self with either the empty list, which has this true structural invariant, or the head and tail, and then we also include the invariant of the head and recursively the invariant of the tail. Okay, so now that we have talked about the unsoundness, I want to talk about a few selected parts of the implementation of type invariance. So first, how do we encode these structural invariants? And this works by having the symbolic inf predicate, which is generic over all types. And then for every type in Rust, we generate an unfolding axiom, which says how to unfold inf for one specific type. So here there's a unfold axiom for the sum to 10 type, just says that for a sum to 10 value, the inf predicate is, as we've seen before, user invariant and structural invariant. And this encoding ensures that we can support mutually recursive types, because we always only unfold one step at a time. So for recursive types, we can unfold the axiom repeatedly as we need. And also this encoding allows us to give different interpretations of the inf symbol in different contexts. And this is useful because it allows us to leverage parametricity. So if we're in a generic context where we don't know the type of a generic type parameter, we can just assume that its invariant is trivial, is always true. And then when we instantiate the type parameter with a concrete type, can give a different interpretation, which actually has the correct invariant for that type. The next interesting part of our implementation is resolution. As a reminder, resolution is how we learn the final value of a mutable reference. And since we use the points of resolution as the points where we have to prove the prophetic invariance, or the points of resolution also are relevant for the soundness of our approach. And so there, originally how resolution was implemented in Creusot is what I call early resolution here. But it turned out that the early resolution algorithm made many programs unprovable. And this is demonstrated here. So the early resolution algorithm resolved a value R if it is dead and initialized. So here in the example, this shows why early resolution does not work in combination with type invariance. So we have S and take a reference R to, oh, there's a typo. It should be S instead of X. So we take a reference R to our sum to 10 value, and then reborrow that reference to create RA. And after we reborrowed R, the original reference R is considered dead and still initialized. So early resolution would resolve R at this point. However, resolving R would also mean having to prove the invariant of that reference. But the reborrowing Ri meant that now the value star or the A field of the reference equals the prophetic final value of RA, which we don't know at this point. And this is also becomes clear if we look at the last line where we write 3 to the pre-borrowed reference RA. So yeah, only after that write we can know the final value of our of the pre-borrowed RA. So resolution must take reborrows into account, and we should only resolve R after we resolved RA after the write to RA, because only at this point we have enough information to prove that the invariant of R holds. So our new approach is what we call late resolution. And late resolution works similar to early resolution, but additionally takes into account whether a value is borrowed or not. And so again, we have the same example where we have a value S, and then we first create a reference R, and then we reborrow R to get a reference RA to the field A. And because after we reborrowed R, it is dead and initialized, but it is borrowed by RA. And so late resolution would wait until R is no longer borrowed, which is after we resolve RA, after we have written 3 to RA. Yeah, like late resolution would only resolve R at the very last line. And now we can prove the invariant of R, since we resolved RA before, which meant that we learned the final value of RA, which is the same as the current value of R, the A field of the current value of R. And yeah, so we can prove that the invariant of R holds. Late resolution allows to prove many programs, but there are still some cases where we get unprovable invariance with resolution. And this is demonstrated by this example. And here we are forced to resolve at a certain point before we can actually prove an invariant. So this function takes 2 references x and y of both of the same type, mutable reference to sum to 10. And so in the first we reborrow x to get a reference xa, and then we reassign x to y. And since before that assignment is the last point that we can resolve x, we are forced to resolve x at this point, which means that we have to prove the invariant of x. But at this point, since we reborrowed the first field, the prophecy xa is unknown, and so we cannot prove our invariant. Right, and so there's another case which is kind of similar to that, also like a technical limitation of resolution right now, and that is functions that return reborrow. So here we have a function which takes a mutable reference and then projects it to its first field. And at the end of the function, we resolve our reference S, which requires us to prove its invariant. But since we return the reborrowed field A, borrowing the field S dot A means that the final value of our result and S dot A are equal. So we would have to prove that the final value of result plus S dot B is 10. But since we don't know the final value of result, we cannot prove this. And this also makes sense because we don't know what the caller might do with the returned reference. And so we cannot be sure at this point that actually the invariant will hold for the final value of S. Okay, so now for conclusion and future work. We presented a solid implementation of type invariance for Creusot. And we achieved our design principles through a novel prophetic encoding for mutable references. And it's fully composable with respect to Rust's type system, also thanks to our structural invariance. But the main question is it actually useful? And proof or evidence for that is that type invariants were used extensively in the verification of Rust iterators, and also that type invariants enable the verification of larger programs by giving us more means of abstraction and encapsulation. Okay, so future work for type invariants in Creusot is that we want to support returning reborrows from functions. That example. But to support that, we would need a new kind of specification, a kind of precondition which says that whatever the caller does with the returned reference, that the caller only changes the returned reference in a way that preserves the invariant of S. This is maybe similar to a assert on expiry but currently Creusot does not support such contracts, so we cannot verify this function. We want to verify more complex programs using type invariants to better test our design and approach, and also optimize the generated SMT, especially regarding quantifiers. So adding these invariant implication after universal quantifiers means that there are sometimes problems with triggers for the quantifiers, and we're still looking into ways of how we could improve generated SMT. All right, that's it from my side. So,
thank you very much, Dominik. We have some time, so if there are any questions, I think Ralph might have had a question, but if there are any questions, we can take a few right now. Yeah, Ralph, please go ahead.
Right. Yeah. So we started discussing this in the chat already. Yeah. First, thanks for the talk. That was fun. That was interesting. I was curious when you mentioned parametricity, because Rust is not in general very parametric on types, at least. I mean, on stable you can look at the size and stuff, and you might not care about that, but specialization completely breaks parametricity, right? So what is this parametricity you are assuming, and why is this sound?
Okay. Going back to the slide. So here, okay. So when we are inside of a function which has a generic argument, then inside this the context where we verify the body of that function, we don't care about the invariant of our argument T. So there we can assume or we just say that our argument has has the trivial invariant true. But in another context of a caller of the generic function, we actually have the proper unfolding axiom, which correctly gives us the invariant of that type. Which also, if we are in a caller which leaves the argument generic, then we would still have a opaque invariant. So assuming that invariants are trivial only happens in the body of functions which have generic parameters.
Yes, and I'm asking how that makes any sense, because like it's an unknown invariant. It might be true, it might be false, it might be something is even, like you have no idea. So what's the justification for the trivial invariant implying it works for any invariant? That's not clear to me.
But how would a function break the invariant of a generic type T? So the only way would be if the type of the argument would actually be a mutable reference. But if we don't know that, then we cannot write to it and cannot break the invariant.
So what do you do that if the T has an any trait bound or something like that, and then I dynamically downcast, and then I know the type, and then
we don't support the any trait.
Or really any trait bound, like not just the any trait.
Oh, okay.
But then at some point we would have a function which specifies the actual type, and this function would have the proper contract again.
Or if I have an argument T and like a function from T to T, but no, I don't know. This is like Rust is not parametric in type, so I don't see a solid soundness argument here, is basically what I'm saying.
Okay.
And Rust tried to use parametricity on types for drop check and failed famously. So
okay, maybe, I mean, so basically just we didn't think of any way how a function could parametrically break a invariant.
Do you have a sketch of a proof, or do you just not have a counterexample?
We don't have a counterexample.
Okay.
Yeah.
Okay, thanks.
Yeah. Are there any other questions? So yeah, so I don't know if you saw this. Oh, Sarah, there's Vitotas that had a clarification, Dominik. Maybe you can ask that, and I think Sarah has a question afterwards.
Oh yeah, is it in the chat? I don't see the chat.
Yeah, so my question was basically just joining the Ralph. So I was confused why it's not just an interpreted symbol instead of true. Because I think that's the so in Prousty we use uninterpreted predicate. And yeah, I think that's why it's fine.
It's a question of, I think it's depending on the perspective of where you're looking at. It's either an uninterpreted symbol or true.
Right.
Yeah.
So
on the definition side, it will be uninterpreted symbol, and basically on the side that sees the instantiation, it will be the actual invariant, the concrete one.
At the definition site, it can be true for the generic parameter, and at the use site, it's going to be an uninterpreted symbol if it's a generic parameter.
Yeah, that's how we do it. I mean, it's basically just an optimization. So by default, it's an uninterpreted symbol. But if we are in the body of that function, we do this optimization where we say, okay, we can assume that its invariant is true.
But why that works? For example, if I call a random method that breaks, like let's say that type has, let's say the generic type has trait bound with a method, let's call it break invariant. And if I call it, then it breaks the invariant, and forbids me from doing that.
Well, there has to be like some function in this like break invariant trait, which actually has a which specifies like a more complete.
Dominik, I think I can give a shorter answer. You're not allowed to write a function called break invariant. As implemented right now, you always have to return a value that satisfies the invariant. There's no getting around that. So
Yeah.
I mean, even if you have a type T with some bound with some trait called break invariant or something, you know, that should be breaking the invariant of the specific type, that the error there is going to be on the implementation of your trait. You wouldn't be able to implement it.
Okay, I see. Yep, thanks.
Yeah. Derek?
Yeah, hi. Thanks for a great talk. I have a somewhat low-level question. So I remember when I played around with type invariants, it made certain things, such as implement an index, impossible, kind of, or like for the way I used it, because then that suddenly becomes a function boundary. I was wondering whether like there existed any works around escape hatches, whatever you want to call them, or if you have any ideas for that kind of escape hatches.
Well, we plan to support having functions which explicitly say that its arguments do not or have an open type invariant. And right now there exists an attribute which you can add to arguments, but right now it's unsound. So we don't enforce any rules which would ensure that you don't abuse this to introduce unsoundness.
All right, thanks.
So it's not an officially supported thing that we can have arguments with open invariant.
Julian?
Hi, yes. I have a question just to be sure I understand correctly. The slide you have about the user invariant on recursive types.
Yeah.
Do you really want the user invariant to be checked even on the recursive calls of the... So here in this example on the tail, it looks to me like you want an auxiliary function that recurses through the type, like the recursor, and you only check the invariant of the element, not the invariant of the recursive elements. So in this case, the tail.
Well, the function is not really it's not really a function. It's more so, as explained here again, we have this unfolding axiom, which just says that the inf symbol is equal to that definition. So we would not actually really recurse here, but do one unfolding step at a time.
Yeah, exactly. But the problem is the second inf on the const line.
Yeah.
If you unfold it, you also get user invariant on the tail.
Yeah, exactly.
Yeah, but I don't think you want that. Or unless it means if you want to specify a list of a specific length, let's say you want to have a user invariant that says you have only lists of length 3. Do you need to make a new type? And then have a user invariant only on the new type and have the list without user invariant? Maybe that's how you would do it, I guess. Or in general, here is because sorted, it's something that works when you recurse. The tail of the list, of a sorted list, is also sorted. But there could be type invariants that don't recurse in the sense of when you have the type invariant on the whole list, it doesn't hold anymore on the tail.
Okay, yeah, that's a good point.
If you want, Dominik, I can provide an answer here.
Okay.
Yeah, exactly. Ralph also answered in the chat, which is the issue is that type invariants are meant to hold on all instances of the type, right? You're taking a subset of the values. So something like a list of length 3 doesn't make sense because a list has a tail, which also must be an element of your type, but
okay, so you
can't
need to
have
make
length
a new
3.
type. Yeah.
Yeah.
Okay.
You would wrap it in a new type that says length 3 lists, and you have the property that it only holds a list of length 3.
Okay, that makes sense. Yeah. Okay, thank you.
Great.
So I think we have time for one more question, if there's anybody. Oh, Ralph is back.
I
Yes.
would take it if I can get it.
Yeah.
But I would let others go first, obviously, because I already had a bunch of questions. No, I have to scroll through this. No, I think it was still about the parametricity point. You said it's an optimization. So in which sense is it advantageous to assume that the invariant is true instead of just having it uninterpreted? Because if you're ever in a situation where you have to prove that invariant out of nothing, clearly something is very weird. You're not supposed to be able to create values out of nothing. That's the entire point. So basically, if you're ever exploiting that the invariant is true, something is wrong. So why is it helpful to assume that it's true?
So basically, we have a optimization where we check whether an invariant is trivial. And if an invariant is trivial, we just don't elaborate, or we don't add an additional. For example, we don't guard the quantifiers.
So Vytautas has a part of the answer here, which is that the desire to be able to do this is it makes the SMT queries smaller, and more importantly, it makes them easier to work with for the solvers.
Yeah.
Yeah. So when possible, you want to be able to get rid of the presence of invariants, especially when they don't bring anything. And so even pushing around uninterpreted symbols can end up causing SMT solvers to go off in weird paths.
Yes, thanks.
I don't know if Ralph has anything to say about that.
No, I mean I don't know SMT
Okay.
solvers. So
Okay. Yeah. Okay. No, I was
thanks,
just
thanks for answering.
Yeah. Well, I'll make one final call for last question, and otherwise I think we'll bring this to a close. And so we will be meeting again at the end of October, more precisely on the 30th, the day before Halloween. That'll be very nice. So any last questions? In that case, thank you very much. And thank you very much to Dominik for this great talk. And we'll see each other all again in October. Bye.